Okay, I'm going to share my thinking on questions 3 through 8 on this chapter 10 packet to finish this up. So, number 3, it's asking for the ketone tautomer of each and all present under slightly acidic conditions. So, whenever you're converting the enol to the ketone, you just have to understand that the proton, it's gonna be deprotonated, and our pi bond is going to shift to the oxygen, leaving the ketone. So if you do this with each of these structures, just think about the proton leaving and the pi bond shifting over to the oxygen, you'll get the product. So here's what I have for all 4 of my answers here for number 3. Also, as I go through this, my answers will be in orange because I did it with this pen. And when I checked my answers, if I got any wrong, you'll see it because it'll be in a different color in purple. Unless I drew arrows, I'll always do those in a different color. But I'll show you which ones I got wrong. So I got all of these correct. I thought number 3 was pretty straightforward. Number 4 says complete the mechanism for the acid-catalyzed tautomerization reaction. Use curved arrows when necessary to show movement of electrons. So I did all my arrows in purple here. So let's see. So we're having the pi bond attack the proton here on the hydronium. So that will leave us with this cation and positive charge on the carbon. And then I'm showing with this arrow, I'm showing the electrons moving into forming the pi bond. Water was the other product after we deprotonated the hydronium. So our resonance structure would be the almost to our ketone, but again, it's protonated here. So my water is going to deprotonate that hydrogen. Electrons shift into the double bond. Actually, I formed the double bond here. I shouldn't have, but I'm sorry. No, we're good. This arrow shows the double bond formation, and this arrow shows the electrons from this bond dumping onto the oxygen, leaving it without its positive charge. So here's the correct answer for the first one. And then the next one, so that was acid catalyzed. This is going to be base catalyzed. So we have hydroxide coming in, deprotonating. It's going to leave us with our anion here with a negative charge on the carbon. And then the resonance structure, again, electrons dump here, going to form a pi bond here, and the pi bond breaks and forms the negative charge on the oxygen. So here's your 2 resonance structures, and then I use this structure attacking the water, and then leaving water as the base here, hydroxide, and then our anion, again, turns into the ketone. And then water was the other product. So that was 5. 6, I believe this is 6. This was kind of fun. They give us all these reagent possibilities, and they want us to fill in boxes to match the reagent. So here's where I got I got one wrong here. So anyway, looking at, here's our starting substrate. So they want us to identify the reagent that turns it into this. So I'm thinking that this is a trans addition of hydrogen. So that would be the metal F, the sodium. This was metal reduction, the sodium and lithium metal and ammonia. And then over here we have the cis addition, so that's that Lindworth's catalyst, so that's J. And then for the next one, it looks like we are adding methyl to the side of this alkyne. So we need a strong base, which is S. So our NaNH2, and then we need to come in after that with methyl bromide, because we have to add that methyl. So that's the one I got wrong. I actually chose A, but that would be too many carbons added. That would have given us an ethyl here instead of a methyl. So next we have they gave us this. They want us to figure out I went this way first. We have 2 strong base equivalents, so that would deprotonate our hydrogen. That would actually eliminate the bromines, and that would leave us with our triple bond. And then thinking, going backwards here, what would our alkane be that would form our alkyne? And that would be, again, this is, since we have bromines here, this is going to be a bromine. So P. Next. So we are going from C2H2 to C5H8. So I drew out C5H8 from C2H2. So we're adding 3 carbons. So that means we have to deprotonate one side of this acetylene, and then we have to come in with 3 more carbons. So we need C, which is propyl bromide. That'll add on the 3 carbons to this side. And then this is acid catalyzed hydration, so we're going to add OH to the more substituted side of this, which leaves us with a ketone on this carbon right here. So there's our picture there for that ketone. Continuing on, we've got, again, we have a ketone formation here from our alkyne. So this is going to be acid catalyzed hydration, so I picked Y here. This is an aldehyde formation, so this is going to be hydroboration oxidation. So that's going to be Q. Here we are, again, we're adding a methyl group instead of our hydrogen here. So again, we need to deprotonate with a strong base with S, and then we have to come in with a methyl bromide, which is H. Next one, we are going from an alkene to, we got bromine, so bromine had to be added, so that's P. Then we're going to, let's see here. What did I do? I guess I looked at the end here and I worked my way backwards. So this, to form this from just a strong base, we would have to have had, what did they do here? They just deprotonated it. So let's see here. I guess, or is this, I'm losing my train of thought here as to why I went backwards here, but I do have, thinking about, let's see here. Oh yeah, I'm missing my bromine. So this should be, no, that's correct. Okay, deprotonate, add, that would be correct. Not really sure. Lost my train of thought on this one, but this does check out with the key. For this one, adding bromine across the pi bond. Yep, bromine's addition to each carbon. And then strong base with water would give us our terminal alkyne, and then strong base with D, which is this 1, 2, 3, this butyl iodide. We'll add on our 4 extra carbons to this side. So I'm going to go back to this one for a second. So strong base would deprotonate, so it would eliminate the bromines, and with water that would give us our terminal alkyne. And then adding another strong base with our methyl bromide would add another carbon on. Okay, so that's what I was thinking. We got this extra carbon here. So, but this reagent here, okay, so this is metal reduction. So I'm thinking that they wanted, this would make more sense if it were sodium and not NaNH2. So I don't know. That's got me a little confused. Okay, next, number 6. Okay, so we got acid catalyzed hydration, so I've formed a ketone on the carbon here. Next, we have just 1 mole of HBr, so this is hydrohalogenation, so addition of bromine to the more substituted carbon. Peroxide's present here, so add the bromine to the less substituted carbon. We got 2 moles of HBr here, so we're going to put both bromines on the more substituted carbon. Those last 3 were all hydrohalogenation. Bromination here, so again, this would be trans addition to the bromine across the pi bond, so trans addition. And then here we got 2 moles of bromine, so trans addition twice, so both carbons get the bromines. Continuing on, got excess hydrogen, lots of hydrogen, so this just essentially turns this into an alkane. Strong base with methyl bromide, that's going to add the methyl group onto the terminal side of the alkyne. 2 moles of HCl, so we're going to add 2 moles of Cl to the more substituted carbon. Here we have acid catalyzed hydration here, so we're going to do, okay, so here we don't have a terminal alkyne, so it's just as likely that the ketone would form on either of these carbons, so that's why we have 2 ketones. So this first product is the double bond forming on this carbon, and the second product is the double bond forming on that carbon. So you'll see that with acid catalyzed hydration with non-terminal alkynes. Here we have the metal reduction, so that's going to be the trans addition of hydrogen. So that's why I have the trans. And then the last one here, we've got, this is D2, that's just deuterium, that's just hydrogen, that's just water. So we got strong base and water. So that's just going to, again, it's going to deprotonate, it's going to eliminate the chlorines and form our triple bond. Next, 7. So again, this is acid catalyzed hydration with an alkyne that's not terminal. So we have just as much likelihood as our ketone forming here as we do here. That's why we have 2 products. So this product would be the double bond forming here, and this product would be the double bond forming here. This is our, again, hydroboration oxidation, so it's the formation of our aldehyde. So we're basically forming our double bond on the less substituted carbon, and again, acid catalyzed here, double bond formation on this, on the more substituted carbon. So that gives us our ketone here. Okay, this is ozonolysis. We get 2 carboxylic acids. So what I do here is I just think about this carbon here and this carbon here were triple bonded to each other, and I piece them together. So that would be this carbon would be here, and this carbon is here, triple bond them together, get rid of the OH and the O, and we're good to go. If you have CO2 present, then that means you had a terminal alkyne. So what I did is I just took the carbon here and the carbon here and triple bonded them. Carbon, 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 pieced them together. And number 8, same thinking here. You've got ozonolysis, so I just took this carbon and this carbon and I pieced them together. So this carbon was here, this carbon is here. Again, get rid of the OH and the O. All right, this is a ketone. So working back, we need this carbon here would be the more substituted carbon on our triple bond, and then this carbon would be the terminal. So that's gone. And then this would be this is an aldehyde, so this would be our hydroboration oxidation. So this carbon should be terminal, so pi bond on that carbon, so this carbon is this carbon. And finally, only one product. We got a ketone here, so the only way that this would work would be that we have two carbons that are just as likely to form the pi bond, the double bond. So this would be our answer here. And I think that's it. Okay, so hopefully that went well. Next week we'll do the test, and we're about done, people. Orgo 1 is about wrapped up. Have a great day.